Hey guys, welcome back. So today we're going to be covering limit laws, algebraic manipulation, and the squeeze theorem. So generally there are three ways we can evaluate a limit. We can do it graphically, by a table, or by direct substitution. And so the limit laws are just rules that we can apply to the limits that we're given so that we can have ways to solve them. So I'm going to really quickly write the limit laws on the board and then we'll go through some examples and explain them. Okay, so these are the 5 limit laws that mainly you'll be using. So, okay, so let f of x and g of x be defined for all x not equal to a over some open interval containing a. Assume that L and M are real numbers such that the limit as x approaches f of x equals L and the limit as x approaches a of g of x equals M. And then let C just be some constant. Okay, so the first limit law that we have are the sum or difference laws. So that's just saying that if we have the limit as x approaches a of f of x plus or minus g of x, then what we can do is actually split those up into its components. So the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x, and that'll just be equal to those limit values plus or minus each other. Then we have the product law. So that's saying if we have the limit as x approaches a of f of x times g of x, we can again split that up into the limit as x approaches a of f of x times the limit as x approaches a of g of x, and that'll just be equal to L times M. And then similarly, we have the quotient law, which just states that the limit as x approaches a of f of x divided by g of x can again be split up into the limit as x approaches a of f of x over the limit as x approaches a of g of x, which is going to be equal to those limit values L divided by M if M is not equal to 0. Then the last two we have are the power rule. So the limit as x approaches a of f of x to the nth power. It's just we can raise all of the limit as x approaches a of f of x, and we can raise all of that to the nth power. And that's just going to be equal to the L, the limit value raised to the n power, and that's for every positive integer n. And then the last one, we kind of have to squeeze it in, but this is the root law. So the limit as x approaches a of f of x to the nth root, we can just squeeze the limit inside of the radical there, and that will just be equal to the limit value to the nth power. And that's for all n, or for all L if n is odd, and for L greater than 0 if n is even and f of x is greater than or equal to 0. So that was a lot of information. So what we're going to do is actually, I'm going to erase the board and then dive into some examples. Okay, so when you're doing limits by direct substitution, that just means you're just going to plug in whatever limit value that you're trying to find. So if we're doing the limit as x approaches 5, we'll just plug in 5 to whatever equation we're given. And so when you do this, one of two things will happen. One, you can just plug in the number just fine, nothing bad or weird will happen. You'll just get a limit value like normal, and then you can continue on. Or something kind of weird will happen, you'll get like a 0 over 0 or infinity over infinity or another indeterminate form like we're going to cover in a couple lessons. And so when this happens, when you get an indeterminate form like that or something that just doesn't make sense, what you're going to want to do is just algebraically manipulate it somehow, which means just beat it into shape, or the ultimate goal is just to convert it into an equivalent expression and then continue taking the limit until you get an answer. Okay, and then two other quick rules that we have before we get example is the constant rule and these are just constant rules. Okie dokie. So this first constant rule just states that if we have the limit as x approaches c, or x approaches a of a constant, it's just going to be equal to that constant value. So let's say we have this, random value 5. So if x is approaching it, no matter how far in either direction you go, 5 is just always going to be 5. So that's kind of the logic behind that limit value, or that limit rule. And then you have the line y equals x, and you just have this some value a right here, the limit as x approaches a of x is just always going to be a, because it's another constant rule like that. Okay, so now we're actually going to get into some examples just to make sense of this. Okay, so example 1. Let's say we're asked to find the limit as x approaches 3 of x cubed plus x minus 4 all over 6 minus 4x. Okay, so the first thing that we're going to want to do is just see if we can directly substitute into this equation. So if we just put everything in, it doesn't look like we're going to get like a 0 over 0 or anything weird like that. So we can go ahead and just use our limit laws. Okay, so the first thing we can do is just use one of our sum or difference laws. So we're going to use that a couple of times. So we're going to split this top portion up, and then we're also going to use a quotient rule, because this is a quotient and we can split that up as well. So we're going to have the limit as x approaches 3 of x squared plus the limit as x approaches 3 of x minus the limit as x approaches 3 of 4. And this is all going to be over the limit as x approaches 3 of 6 minus the limit as x approaches 3 of 4x. So what we did was we just saw the different limit laws that we could use and then just applied them. So we had a big quotient, so we just took that. We could have done, the quotient and then just split it up into, each of its components, but I think talking through it, you get a good sense of the limit laws that we use and why we can apply them. Okay, so we have the limit as x approaches 3 of x cubed, so we can just go ahead and plug that in. So we'll get 3 cubed. And then we have the limit as x approaches 3. That was one of our constant, if y is equal to x rules that we just had, so that's just going to be 3. We can plug that in. And then another constant rule, the limit as x approaches 3 of 4, it's just always going to be 4 because 4 is a constant. Okay, so we have, again, the same constant rule. So the limit as x approaches 3 of 6. 6 is always going to be 6, so we can just put that down. And then we can just directly substitute 3 in for the 4x. So 4 times 3. So we'll just have 27 plus 3 minus 4. And then we'll have 6 minus 12. And so this is going to be equal to 26 over negative 6. So if you're asked this question, what you want to do is just break down into the limit laws that you can use and then just kind of methodically work through them. Okay, so we're going to do one more example before we get into ones that we can't just directly substitute this easily. Okay, so example 2. We're asked to find the limit as x approaches 3 again of 5x squared plus 2x all over sine of pi over 2x. Okay, so just like in the case that we just had before, there's a couple limit laws that we can start applying. So first we could just split up the numerator and the denominator using the quotient rule. So we'll have the limit as x approaches 3 of all of this, of 5x squared plus 2x, divided by the limit as x approaches 3 of sine of pi over 2x. And then we could further split this up using the sum and difference laws on the top. So we could have the limit as x approaches 3 of 5x squared plus the limit as x approaches 3 of 2x. And this is still all over the limit as x approaches 3 of sine pi over 2x. And then from here we can just directly substitute. So we'll just plug the 3 in for the 5x squared, so it'll be 5 times 3 squared. And then plus 2 times, plug the 3 in, 2 times 3. And then for this one, we'll just do the same thing. So we have sine of 3 pi over 2, plugging in the 3. Okay, so now we're just going to have 45 plus 6 on top. And then we're just going to have negative 1. And so, to further simplify, but that's just the gist of how you break limits that you're given into their components and then work through and solve them. Okay, so now we're going to get into some methods of algebraic manipulation for when limits don't necessarily work by just direct substitution. You might have to do a little something to them to make them, able to actually get the answer. Okay, so there are 3 methods that we'll be covering in this, section: factoring, rationalizing the numerator and denominator, and simplifying a complex fraction. Okay, so for factoring, the main goal is just to factor and cancel something out. So I'm just going to do a quick example to show you what I'm talking about. So let's say we're asked to find the limit as x approaches 2 of x squared minus 4, x minus 2. Okay, so if we try to do what we did before, and just directly plug it in, we'll get 2 squared, which is 4 minus 4, which is 0. And then we'll get 2 minus 2, which is 0. So we have a 0 over 0 kind of situation here, which tells us that we might want to look into factoring and canceling something out so that we can actually solve this. So what we're going to want to do, is split this x squared up into its components. That's going to end up being x plus 2 and then x minus 2. And what that does is actually allow us to cancel out these x minus 2's. And so what we're left with is just x, the limit as x approaches 2 of x plus 2. And then we can go ahead and use the limit laws that we've been working on. And just further split this up a little bit. The limit as x approaches 2 of x plus the limit as x approaches 2 of 2. And so this is these are both actually examples of our constant laws. So the limit as x approaches 2 of x will just be 2. And then since 2 is just always a constant, that will also be 2. So the answer to this limit, as the limit as x approaches 2 of x squared minus 4 all over x minus 2, is actually going to be 4. So what we did was we saw that we couldn't directly substitute without getting an indeterminate form. So we decided to factor something and just see if that works. And it ended up working. We actually canceled the x minus 2 with the x minus 2 in the denominator. And then we were just able to directly substitute the limit in. Okay, let's do another example. Okay. So, let's say we were asked to find the limit as x approaches 0 of x to the 4th plus 2x cubed minus x squared, and then all over x squared. So, similarly to the last example, if we just try to plug in x is equal to 0, we're going to get a 0 over 0, which is just telling us that we need to do something to cancel out or make it into an equivalent expression so we can take the limit again. And so in this case, we can actually factor out an x2 over in the numerator. So if we have an x squared, so we have an x squared plus 2x minus 1. And that's actually going to cancel with the x squared we already have in the bottom. So we can go ahead and cancel that out. And then we're going to have the limit as x approaches 0 of x squared plus 2x minus 1. And then we can again use the limit laws to split this up. So we have the limit as x approaches 0 of x squared plus the limit as x approaches 0 of 2x minus the limit as x approaches 0 of 1. Okay? So because this, we can just directly substitute in, we're going to substitute 0 in for x squared, so that's going to be in 0. The limit as x approaches 0 of 2x will also end up being 0. And then because the limit, minus, the limit as x approaches 0 of 1, 1 is always going to be a constant, so the answer is just going to end up being -1. Okay, so when you're doing factoring, you might have to use, different factoring techniques in order to cancel something out, but the main idea is you want to take a look at what you're given. If you can't directly substitute in, try to find a way to factor out a common factor and then cancel those so that you can directly substitute and find the limit value. Okay, so that is one technique for algebraic manipulation. The next technique we're going to cover is rationalizing the numerator and the denominator. Alright, so the last couple sections we're going to cover are rationalizing the numerator and denominator, and simplifying complex fractions, and then the squeeze theorem. So what does it mean to rationalize the numerator or the denominator? Rationalize just means to get rid of any roots or radicals. So the way that you do this is to multiply the top and the bottom by a value so that after you're done, the fraction does not have any more radicals in a problematic area. Okay, so I'm going to show you an example, and then hopefully that'll make a little bit more sense. Okay, so we have the limit as x approaches 4 of the square root of x minus 2 divided by x minus 4. Okay, so in this example, if we just went ahead and directly substituted 4 in, we'd actually get a 0 over 0 limit. And so we want to avoid that. And so what we're going to do is actually multiply the top and the bottom by the conjugate of the numerator, because that is the place that there is a radical. Okay, so just quickly wrote down the square root of x plus 2 over the square root of x plus 2. And so anything that looks like this, we're allowed to do this because, one, this simplifies down to 1. And so we're not really changing this expression, we're just simply manipulating it so that it's easier to work with and we can actually get an answer for the limit we're trying to solve. Okay, so I did this because you see a negative here and you see a positive here. What this is going to allow us to do is after we multiply the numerator out, it's actually going to cancel the radicals that we're trying to eliminate. Okay, so rewrite the limit as x approaches 4 of the square root of x times the square root of x is just x, and then we're going to have outer, so plus 2 times the square root of x, minus inner, which is negative 2 square root of x, and then minus 2 times positive 2 is just 4, and then we're just going to leave the bottom how it is, because it's actually going to end up doing some nice things for us. Okay, so we have the square root of 2, or no, we have 2 times the square root of x minus 2 times the square root of x, and we can actually end up canceling that. And so we'll end up having the square root, or the limit as x approaches 4 of x minus 4 over x minus 4 times the square root of x plus 2. And so the reason I said just leave this multiplication just kind of as is because after we cancel and rationalize the numerator, we can actually use the remainder of what's left of that to cancel and make things easier for us in the denominator. So we're going to cancel the x minus 4 in the numerator with the 1 in the denominator, and then just be left with the limit as x approaches 4 of 1 divided by root x plus 2, and then we're going to use our limit laws, so we're going to split up this fraction, so the limit as x approaches 4 of 1, and then we're going to use sum rule in the denominator, so the limit as x approaches 4 of radical x plus the limit as x approaches 4 of 2. And so the one up top is just going to be one of our constant limit laws, so that's always just going to remain 1. And then we can just directly substitute in for the square root of x. So the square root of 4 is just 2. and then another constant, so it's just always going to be 2. So the answer to this problem is just going to be 1/4. So I hope this example gave you a little bit more clarity about how to approach something that has a radical in the numerator or the denominator. So figure out a value that, and usually the conjugate, that's what this is called, the conjugate, just means that after you multiply all of this out, you're getting rid of these radicals. So after you multiply and FOIL, make sure to just kind of leave as is, so you don't have to actually multiply what's in the denominator or in the numerator if you're rationalizing the denominator. And then just make sure that you can just cancel this out and then just directly substitute and use your limit laws to break things up even more. Okay, so the next thing we're going to cover is simplifying a complex fraction. Okay, so let's say we have something like, we're asked to find the limit as x approaches 1 of 1 over x plus 1 minus 1/2 all over x minus 1. Okay, so when you first look at it, it looks kind of ugly, right? I mean, we have this x minus 1 is really the problematic thing in the denominator, because if we just simply directly substitute in, we're going to get all of this divided by 0. So we're going to want to figure out a way to just cancel this by simplifying what's in the top. Okay, so we're actually going to multiply everything by 2 times x plus 1. And as you can see, like the last example we had, this is just going to simplify to 1, so we're not really actually changing the expression. You want to be careful of that you're actually not making a different expression when you're trying to simplify. Okay, so if we have 2 times x plus 1 on the top, it's going to be over x plus 1, then minus 2 times x plus 1 on the, I just multiplied that through, and then we're just going to leave the x minus 1 times the 2x plus 1 on the bottom. Okay, so rewrite the limit as x approaches 1. Okay, so now we can just cancel these out, and then we can also cancel this out. And so we're left with, on the top, the limit as x approaches 1 of 2 minus x plus 1. And then on the bottom, we're just going to leave it as is. 2 times x plus 1. Okay, so now let's just simplify the top a little bit more, so it'll make it easier for us down the road. Okay, so 2 minus 1 is just going to be 1. So we're going to have minus x plus 1. And then we're going to have x minus 1 still on the bottom, and then 2 times x plus 1. Okay, so now we still have the x minus 1 on the bottom, and that's the thing that we want to cancel. So what we're actually going to do is pull out a negative in the numerator. So we have negative 1, we're going to pull that out. So we're left with x and then a minus 1, which is going to cancel nicely with the x minus 1 that we've been trying to cancel on the bottom. So we're going to cancel these. That makes our life a lot easier. So we have the limit as x approaches 1. And then we just have, we're left with a negative 1 on the top, and 2 times x plus 1 on the bottom. Okay, so now we can use our limit laws, now that we can just directly substitute in. We're going to use our limit laws to simplify and figure out what this limit value is. So we have a quotient law that we can use. So let's use that. And then I'm just going to multiply this out, so it's 2x plus 2. So 2x plus 2. The limit of x approaches 1. Okay, so this on the top is just going to be, oops, kind of sideways, so let me write that. Okay, so the limit as x approaches 1 of -1. And then we can actually, after we multiply it out, we can use our sum law. So the limit as x approaches 1 of 2x plus the limit as x approaches 1 of 2. Okay, so now we can evaluate the limits. So this is going to be a constant, so it's going to stay a constant no matter what. And then we can directly just substitute the 1 in, so that'll be 2, another constant plus 2. So we actually get the answer to be -1/4. Okay, so the deal with simplifying complex expressions is you have to get a little bit creative. So in this case, we multiplied, the top and the bottom by the same number, so we're not actually changing the expression. And then the goal that we had in mind was to make sure that we could figure out a way to cancel this x minus 1. And so always make sure you have your goal in mind so that when you're manipulating algebraically, you have a clear path about how you want to accomplish what you want to solve. Okay, so this is kind of the wrap-up of the algebraic manipulation section. So to summarize, when you're doing limits, first try to directly substitute. And if you end up getting like a 0 over 0 or another indeterminate form, that's when you have to use algebraic manipulation to evaluate and, to mold the expression a little bit and make sure that you can use different techniques like factoring, rationalizing the numerator, denominator, and then simplifying complex expressions so that you can actually get the value of the limit. Okay, so this last section will be on the squeeze theorem. Okay, so the basic idea of the squeeze theorem, as the name implies, is that we're evaluating limits by squeezing them in between limits that we know the value of. So if we have a limit that we don't exactly know the value of, but we know that a limit above it and a limit below it converge to a single value, that means that we know that we can squeeze the limit that we don't know in between the ones that we do know. Okay, so I'm going to draw an example of kind of what I'm talking about. So let's say we have this value a, and we have this kind of, we're going to call this h of x. Then I'm going to do another color. So this one is going to be g of x. And then use black for our, oops, okay, we're gonna make this a little bit better. Okay, it's supposed to be a, we're gonna move our a over here. Okay. Okay, so I'm going to write out what the squeeze theorem says, and I'll explain it. Here, okay. So let f of x, g of x, and h of x be defined for all x not equal to a over an open interval containing a. If f of x is less than or equal to g of x, which is less than or equal to h of x, for all a not equal to x in an open interval containing a, then, and the limit as x approaches a of f of x equals the limit as x approaches g of, or h of x equals L, then we know that the limit as x approaches f of x, or g of x. I don't know what f of x is. G of x is equal to L. Okay, so I'm going to break this down for you. Okay, so we have, oops, this is f of x, and then this is g of x. Okay, cool. So we have this value, this open interval containing a, right? And then we have h of x on top, g of x on bottom, and then f of x is just squeezed in the middle, which is, it's called the Squeeze Theorem, or you might hear it called the Sandwich Theorem. It's just because it's sandwiched or squeezed in between these other two values. Okay, so it's saying we need f of x, g of x, and h of x to be all defined for all x's that are not equal to a over an open interval. And so f of x needs to be less than g of x, which needs to be less than or equal to h of x. And then it's saying if we know that the limit of f of x is equal to the limit of h of x. No, I did have it right the first time. My bad. We're going to switch these back. Sorry. So, if we know that the limit of f of x is equal to the limit of h of x, then we know that the limit of g of x is equal to L. And so what that's saying is, if we know these other values, and we know that all of them are, if we know that the one that we want is squeezed in between the ones that converge to a single value, and that they're all defined, then we know that the limit that we're trying to solve has to be that value. Okay, so hopefully that made sense. Sorry for the confusion with the diagram. I'm going to give one quick example and then we're going to wrap up. Okay, so we're asked to find the limit as x approaches 0 of x squared times sine of 1 over x. Okay, so if we're asked to find something like this, we know we should probably use the Squeeze Theorem. And that's kind of characteristic by, the sine of 1 over x. It might be another trig function that they're asking, but the way to do it is just to think about, just rationalize for a second. So we know that sine of x only takes values from -1 to 1, so we can use that. So if it's sine of 1 over x, we know that it also has to take values between -1 and 1. Okay, and then we know that we have an x squared, so we can just multiply everything by x squared. That's not changing this inequality at all. Okay, so now we can take the limit of all of these. So we're just going to apply the limit as x approaches 0 of negative x squared. We're going to apply it to the one we're actually trying to solve. And then we're going to apply it to the one on the outside. Okay, so if we just directly substitute the limit in, we know that if we put 0 in for x, it'll be 0 for the negative x squared, and it'll also be 0 for the x squared. Okay, so we're going to have the limit as x approaches 0 of x squared is going to equal the limit as x approaches 0. And I'm just going to write out how we solve this using one of our limit laws. And then the limit as x approaches 0 for, okay. So we pull a -1 out. So it's just still the limit as x approaches 0 of x. And then from one of our limit laws, we can just pull this, we can pull the limit in and then push all of that, and then we're going to do a squared. That was our root law that I wrote up in the corner. Okay, so 0 times -1, still 0. These are the same number, which is 0. And so you could write on your paper, by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. Okay, so hopefully this video helped you learn about how we can use the limit laws to evaluate the limits that we're given, and also use algebraic manipulation to evaluate certain expressions that are resulting in indeterminate forms, and then also a little bit about the squeeze theorem. So in a couple more videos we're going to do a limit review, and I will cover all of these topics in greater detail so we can get more practice. Thank you.